Alaikum and good evening everyone. Welcome to day 4 of the course with the new and exciting module Application Discussion. So without any further delay, I would like to invite our honorable course instructor Dr. Mustafa Ali Mursi.
Assalamu alaikum. We will talk today about, as I said, the application. We will have part of the applications today in today's session. And I hope if any question regarding the last lectures or sessions, you are welcome to ask, please. Anything was not clear in the previous sessions? Anybody has a question regarding the last sessions? Okay, that's great. So today we'll talk about some of the applications of the ultrafiltration. Yes? Okay. Today we'll talk about some applications for the ultrafiltration. We'll start first with the physical pretreatment, like for example, in the application of drinking water or potable water from surface sources like rivers, like lakes, or even from underground wells. For just, as I said, standard filtration for potable water, or even for the pretreatment of reverse osmosis feed water for desalination plant. Both of them are identical, okay, regarding, as I said, a physical pretreatment. The main task of it just to remove all suspended particles with different sizes, especially the fine particles, as I said, which is less than 2 micron grain size. Okay. So first, let's see this. We have several techniques to measure the suspended solids or the TSS for the purpose of filtration. We have a reverse osmosis widely known technique, which is the SDI measuring technique, or the SDI meter, which we can see here in the corner. Let's get it bigger like that. So SDI technique, and we have the turbidity, and we have the total suspended solids. Okay, total suspended solids. All this included in the pretreatment, as I say, for desalination, or even in the filtration systems. We'll talk about each one, as I said, separately. For the SDI, we can find this instrument which consists of a pressure regulator to control the operating pressure of around, or the applied pressure of around 2 bars. And in the same time, this filter housing, it uses filter paper 0.45 micron, as we see it. And it's from polyamide, of course. And of course, the necessary hoses and measuring flask of around 1 liter, or beaker of 1 liter, container 1 liter size. Okay, we already fixed the filter. In some techniques, we measure the weight of the filter paper, and then we start to measure the flux in time unit. For example, we have this container 1 liter. We need to check how many minutes required, or how many seconds required for the filling of this such a volume. This will be T initial. This will be T initial, the initial time. After 15 minutes, which is the time unit, we start to measure again the flux and the time elapsed to fill this, the same container, okay? And it will be the time final. If we already put all the parameters in this, we will have a value. This value for reverse osmosis membrane should be less than 5, and in some types of membrane should be less than 3. So this widely known as silt density index. Why we use the term silt? Because as I said, the silt size range between 64 micron down to 2 micron. Why we choose this type, this range specifically? Because for micron filtration, the amount of TSS to be removed should not exceed 2 ppm. So for reverse osmosis plant, nanofiltration plants, the amount of suspended solids coming to or passing by the micron filtration should not, retained by micron filtration should not exceed 2 ppm. Otherwise, I will have a very high interval of exchanging filters. I need to replace filters frequently, which is cost-wise not okay for the operation. It increases the operation cost, and of course, it is little bit trouble for the desalination unit, because interrupted time and in the same the cost of the filters. So as I said, this kind of measuring for the SDI or the silt density index, just we use it for measuring or of a specific range of size. So we have, as I said, the media filtration. We can remove particles down to 30, 20 micron, but less down than that or less than that, it's medium and fine silt will be load for the micron filtration, will be present as a load to be removed by micron filtration, which, as I said, in total should not exceed 2 ppm. For some cases, in some cases, we have too much clay in the groundwater or contaminants during the flooding period in the river. So all this suspended clay should be less than 2 micron. And in such a case, we need much efforts to remove it, either by the application of flocculant and coagulant, and in the same time can be used by the alternative procedure, which is ultrafiltration. Okay, so ultrafiltration in such a case is the optimum solution for the removal of these fine particles less than 2 micron. As I explained before in the beginning of this course, we have the particle size, as I said, which we can find in surface water, in groundwater, in surface water as a feed for desalination, or surface water for potable water clarification plants. We can find the different grain size ranges. The grain size range over 2 millimeter, we call it gravel. From 2 millimeter till 64 micron, we call it sand. It has, of course, coarse, medium, fine. And for the particles range less than sand size, we call it silt size. It ranges between 64 micron down to 2 micron. Less than 2 microns, it is a clay size, as we say. So this nomenclature just to be used as a grain size ranges, not as a composition, to represent grain size range, not composition or mineralogic constituents, or as I said, chemical compound. So these particles, as I said, can be from different origins, it can be with different shapes, it can have, as I said, different, as I said, structure, like for example, here rounded, angular, here in the form of flux, which is less than 2 micron. Normally, the clay mineral, which is around 7 types of groups of clay minerals, can exist in this form as we see. So it is used, as I said, we normally remove it by coagulation and flocculation, and it's easily removed, as I said, by media filter if it is over 2 microns. If it is less than that, so we have just to pass by ultrafiltration. Of course, as I say, if we are applying pressurized system, much care should be about the maximum size for the maximum particle size, which will pass in the module or in the membranes, around the membranes, just not to have much, as I said, coarse particles can be entrapped between the fibers and cause fouling problem or problem in the element itself. If it is open system, we have, as I say, very wide range of particle size to be removed between, as I say, 5 micron, 5 nanometer, 10 nanometer, up to 1 millimeter, In pressurized system, we have very limited range, as I say, between 5 to 10 nanometer up to 150, 300, as we saw in the figure yesterday explaining the system operation. But actually, it should be in the range of 150 to 200 micron. Okay, this is for most of the manufacturer. So this is, as I say, the use of ultrafiltration in the physical treatment for the removal of particles. We have, of course, turbidity, measurements, or as I said, TSS measurements or SDI. I prefer overall to have the TSS as a device for measuring of all suspended particles to cover all the range between, as I said, 5 nanometer up to 1 millimeter or whatever. Okay, some of the devices use optical sensor by laser, can measure, as I said, the particle shape, the particle, as I said, make complete like inventory for the particle size ranges. For example, between 5 nanometer till 20 nanometer till 40 nanometer and so on. So it can give very good estimation or calculation for the dominant particle size in the system. Other application will be for the wastewater treatment. The wastewater treatment application include 2 types of application. The first one is the MBBR plants, membrane bioreactor wastewater treatment plants. And the second is the tertiary filtration instead of media filtration in wastewater treatment plant. So this is the most dominant, as I said, or widely used applications for the ultrafiltration membrane in plants. In the MBR plants, we can just summarize the system as follows. the wastewater coming to screen for the removal of coarse waste, and then go to anoxic tank for the removal of nitrate and nitrate to remove oxygen by anaerobic bacteria, and of course just to convert all to nitrogen gas, which will be expelled to the atmosphere in the next, as I said, tank. The next step for it, the detention time for the anoxic zone or the anoxic stage in the wastewater treatment plant can be between 1 hour to 2 hours detention time. During it, we measure what we call, as I said, the ORP, oxidation reduction potential, just to keep it within pre-selected range. Let's say the pre-selected range is between minus 100 to 200 millivolt. This is the optimum for the operation of such kind of anoxic bacteria. Less than that, we will start to have the medium itself too much reduced, what we call it ioxenic. So we have, as I said, oxic or aerobic zone, which is over 200, where oxygen can exist. Less than 200 millivolt to minus 100. This is, we call it anoxic zone. Under 100, minus 100, this is ioxenic zone, in which all reduced species like hydrogen sulfide can develop easily, and ammonia. So as I said, the wastewater treated in this anoxic zone for 1 hour for the process which we call denitrification, the removal of nitrate and nitrite, and after that it is displaced, as I said, by another amount of raw sewage. It's continuous process, as we know. Raw sewage enter and push the wastewater, which passed already the anoxic process, to the other compartment or chamber. And the other compartment, which is the MBR reactor, the MBR reactor. Okay, this is the main stage during which we have, as I said, the treated water. We have here enormous amount of sludge carrying, of course, microorganisms, which can be bacteria, can be flagellates, can be just other kind of microorganisms. Very wide variety of microorganisms can exist. As I said, each type has a certain function for the remover or just oxidation or of some pollutants. Some are acting on sulfur, some acting on phosphorus, some acting on hydrocarbons itself, protein, carbohydrates, just to convert all to carbon and sulfur dioxide and nitrogen as nitrate, exactly, which is the end product of this treatment process. So let's focus here, as I say, about this stage in which the treatment process, it can be all of us or most of the people working in this field understand that if we are saying MBR units, this means submerged ultrafiltration membranes, which is not correct. Okay, just as I say, it has advantage over the pressurized system, that it can handle very high value of TSS, very large content of suspended solids. Okay, it can reach between 4,000 to 10,000 ppm of suspended solids easily. Okay, suspended solids, it means that sludge, which has, of course, microorganisms. This means much number of microorganisms, which can already be used for the removal of organic matter or the pollutants in the wastewater, or able to treat the wastewater with high organic load and in the same time in short time or shorter period, because as I said, much food and in the sorry, less food and much microorganisms. Any question? Okay. As I said, this is in the case of submerged, as I said, membranes, which we can see here. The submerged membrane, it can be ceramic membrane, it can be polymeric membrane, flat sheet, or hollow fiber, placed in the MBR tank, as we see, and we have the sucking pump, like the standard system, which we explained before in the previous session. Started to suck, as I said, the water, the clear water or filtered water through the membrane surface. If we considered about the flux range in such application, we are talking about for polymeric membrane in the range between 10 to 18 or 20 uh, just liter per square meter per hour. So we are talking about a polymeric membrane which has a flux rate between, it should have a flux rate between 10 to 18 or 20 liter per square meter per hour. But what about the ceramic membrane? In such a case, also ceramic membrane should have limited flux, not to have permanent fouling in such a case. Or I have to do frequent CEB, chemical enhanced backwash for it. So we are driving with the ceramic membrane with a flux range So we are driving with, as I said, ceramic membrane with a flux rate between 40 to 80, between 40 to 80 liter per square meter per hour. Okay. In this process, as we see it here, we have, of course, let's go. I got your question. I will explain to you. We have this anoxic zone. It acts also as a clarifier. Okay, so we have, as I said, sludge precipitate, and in the same time, sludge return to it to regenerate, as I said, or sorry, to continue the degradation process. So we have, as I said, in this step, let's say, here anoxic bacteria, here oxic bacteria. We have a set of air diffusers to afford oxygen, dissolved oxygen. Dissolved oxygen is monitored to be between 1 to 3 ppm. Okay, in the leaker here in the MBR tank, and we continue sucking of fresh or filtered water from the tank. So in turn, we have here an increase in the suspended solids. The amount of sludge or suspended particles increase gradually. In such a system, we pump the sludge out to sludge holding tank frequently with time interval. Like what? For example, every 15 minutes, the pump operated work to start to pump some of the leaker in this tank to the sludge holding tank, as we see. Okay, so the sludge collected in this tank, it has of course, air diffusers to keep to guarantee the depletion of organic matter in this tank. But from time to time, we have to switch it off because it's a continuous process. It has, as I said, a continuous removal process from for the leaker from this tank to the sludge holding tank. The sludge holding tank, the aeration stopped, and then the sludge started to precipitate. So a scam system or pumping system take the clear water from the top back to the anoxic tank again, or to the MBR tank. Okay, so we have here continuous thickening of the activated sludge in this process. Meanwhile, in the same time, also we have to bump the sludge again when it started to increase in volume back to the anoxic tank for further degradation process. For further degradation process. So again, we have here the anoxic tank, the raw sewage added to it, and in the same time, as I said, displacing the leaker or the wastewater to the next tank. In the next tank, it has increasing continuously, increasing, as I said, sludge content or total suspended solids content. So we have to bump from this tank. We have to bump from this tank the leaker inside, okay, the solution inside. We have to bump it continuously with fixed interval. For example, every 15 minutes, 5 minutes, I will start to bump it to the sludge holding tank, or in the other direction to the anoxic tank. Okay, so this is returned sludge line. This is returned activated sludge, returned activated sludge, returned activated sludge. We bump it, as I said, from this MBR tank back with the organic matter, of course, in it, again to the anoxic tank for further degradation. It is recirculate, and in the same time, I take part of this leaker continuously, and I just bump it or keep it in the sludge holding tank. The sludge holding tank has a cycle of stagnancy, okay, where the aeration stopped on it, and the sludge started to have thickening in the bottom of the tank. The clear water bumped back to the anoxic tank or this aeration tank, the MBR tank. So I hope this is clear for the process. It is continuous process, and it has the advantage that it is working or operating with very high TSS content. This is you cannot achieve in other procedures for wastewater treatment, okay? And in the same time, the high content of sludge with microorganisms make it possible to shorten the treatment time or the period of wastewater treatment elapsed. So instead, for example, in extended aeration, to have it around 16 to 20 hours, we have, as I said, other techniques which can make it in just 3-4 hours or even less in such a case. So this is, as I said, with the submerged membrane. Of course, the backwash can take place every 15 minutes, every 20 minutes, according to membrane manufacturer in such a case. Let's go to the other type, which is, as I said, the side stream, the side stream, which is exactly as I said. Few people know that the pressurized system can be used in such, as I said, application. No, I saw already in one trade fair in Amsterdam, Aquatech, one company exhibiting such a vertical, as I said, micro ultrafiltration membranes with a huge diameter of around 30 centimeter, 40 centimeter, something like that, and 6 meter height. So it is, of course, if we checked the ultra filters or the hollow fiber itself, we can find it, as I said, with big diameters, as we explained before yesterday, that it can have 5 millimeter, even 8 millimeter diameter, just to avoid blocking of this, as I said, fibers. What you mean by sludge excretion mode? how sludge excreted? Please answer me, Ahmed. What you mean by slide excretion mode? As I explained, it's continuous process, okay? And as I said, this process, we keep, as I said, bumping the leaker here to two direction, one to the anoxic tank and the other one to the sludge holding. Okay, this is regardless the backwash process. The backwash process can take place in any time. Okay, it will not cause much dilution due to that. And in the same time, we have, as I said, two types of aeration system. One connected to the hollow fiber membrane cassette, or the ceramic membrane, or the flat sheet, as I said, the ultrafiltration, let's say, membrane, which, as I said, the coarse bubble diffusers and fine bubble diffusers just for the microorganisms in the activated sludge existing in the tank. Yes, please, Ahmed, go ahead.
I thought, doctor,
I cannot hear you clearly, Ahmed. Hello. Hello. Hello.
Dr. Mustafa,
You hear me?
can you hear me now? Is my voice clear?
Yes, your voice is
I thought, doctor, that the two
very
modes
clear.
are
Go ahead.
working. Can
Which
you hear me?
mode?
I thought, doctor, that the two modes, the sludge pumping out and the backwash, they are working separately. I thought that you are connected. The two modes are connected to each other. That's my question. But it's clear now. The washing backwash mode is not connected to the pumping out sludge.
Backwash also. You understand? It's not separate pump. It's not separate pump. We use just a control valve. In most of the cases, filtration application, you understand, we are saving a little bit. If I give yesterday the demo, okay, the demo version, which is showing two pumps, one for operation, one for, as I said, backwash, one for sucking, one for backwash. No, we can use only one pump and just the valves play. Okay, we can change the direction by set of valves to make the, as I said, to be from the filter water side to be in the inlet, and to pump, as I said, to the opposite direction for backwashing. So it is just, as I said, playing with the valve. You can use one set of pumps for the operation and the backwash at the same time. Is it clear? Do I answered you or not? Or it's a little bit confusion?
Right, doctor, it's clear. It's crystal clear. Thank you.
Yes, okay. So we are using, as I said, one set of pumps for backwash and for operation, and we can just play with the valves to close in one direction, open in another direction, and as I said, one sucking from the membrane, one sucking from the filter, and one bumping, as I said, to the tank, one bumping to the filter in opposite direction. So as I say, we can just handle it like that. Okay? So for the other side, as they said, in the Sidestream system, we have the same. We have the aeration tank and the leaker. As I said, it is bumped to the vertical hollow fiber membrane, as we see it inside pressure vessel as a pressurized system. We should consider that here in the submerged system, we run with very high concentration. It is the most or the highest concentration in wastewater treatment plants which we can have. Okay, but for the side stream, it should not exceed really like maybe 200 or 150 ppm, something like that, which is really tiny amount. For this, everybody doing, as I said, MBR plants just recommend to have, as I said, the submerged system instead of the side stream system. Okay, but I just show it here because, as I say, it is still possible, and also with coarser hollow fiber tubes or membranes, it became a little bit more easy because you can go with higher concentration of TSS, as they say, relatively compared to the other fine hollow fiber tubes. Okay, so this is in general for the MBR application. If we consider the tertiary filtration, it's just a filtration process as we explained for the particulate removal or any other filtration process for fresh water, for drinking, potable water, or for desalination feed. So I hope this is clear, this point. We will see this figure showing, as I said, the comparison between both of them. We have, as I said, this side stream, we have the bioreactor, as I said, the MBR, the bioreactor, and the sucking pump suck through the membrane to have a permeate, and as I say, it can be, as I said, go again. This is, in such a case, which system we are doing? It's cross flow. It's cross flow, not dead end. Okay? We should consider that in such a case, we are operating with cross flow. It is continuous process. Okay? We suck from the bioreactor, pump to the ultrafiltration membrane. It is, as I said, cross flow application. Then the little bit retentate, we call it retentate as we agreed, higher concentration, as I said, liquor, go back to the bioreactor. So it is continuous process as we see. So for the side stream, we can use both dead end, and in the same time, we can use cross flow. But for the pressurized system, highly recommended to be, as I said, the cross flow application. For the submerged system, of course, it is dead end, just dead end filtration. So I hope this point is very clear for you. If anybody has a question, because we will move to the next point, the third point, which is very difficult, and I hope really we can get it easy. Okay? So any question till now? Any question? So let's go to the third application. Let's go to the third application. Any question regarding the previous ones? The third application is the removal of iron, manganese, cadmium, arsen, most of toxic divalent, lead, and radioactive species like radium. Hello? Hello? Radioactive species like radium, uranium, and thorium. Okay, so the main concern for us, as I said, in such application is the removal of iron, manganese, and in the same time radioactive material and the toxic divalent species in the water. The researches for such applications was started, as I said, especially for radioactivity removal since 1974, where they already developed a special technique for the removal of radioactivity or radioactive material using iron, manganese, hydrous oxides, for the removal of thorium, uranium, radium, other radioactive and, as I said,